Hello, in this lecture we will be talking about stellar evolution and we will be beginning with the Hertzsprung-Russell diagram of clusters. So, what is shown in the slide is a Gaia HR diagram of a very large number of stars, and one can see that there are stars along the main sequence band, there are stars towards the giant region, and there are white dwarf stars which fall on the lower left corner of the HR diagram. And this HR diagram, as you can see, there has a number of colors because these colors represent the density of stars. In other words, it tells us which region is more populated as compared to the other regions. Main sequence band is the most populated because the yellow color indicates the maximum density, the red is the intermediate density, and the black represents the lower density regions. That means, relatively less stars occupy these regions. One can see that these bands and these patches are quite extended because this is an HR diagram of a very large number of stars, and therefore, there could be various effects which could be creeping in, and if we want to study the evolution of stars, one can use the HR diagrams, but one has to remove these effects as far as possible. For example, one can study stars which are at the same age or at having the same chemical composition, but if one wants to study such kind of stars, one has to isolate a group of stars with the same age and the same chemical composition, and for this we look towards clusters. So, clusters represent groups of stars which are born at approximately the same time from the same molecular cloud, and therefore, they have the same age, approximately the same chemical composition, and therefore, the same distance. And therefore, if you want to study the stars of the same age, we look towards the HR diagram of clusters. So, clusters in our galaxy, that is Milky Way, are broadly categorized into two types. One is open clusters and the other is globular clusters. So, open clusters are found in the disk of the Milky Way. Now, our Milky Way galaxy is a spiral galaxy, as we all know. It and most of the stars are confined towards a disk. However, there are stars and groups of stars which are also above and below the disk, that is known as the halo. But these open clusters are found in the disk of the Milky Way. It comprises groups of stars which vary from hundreds to thousands. And these are stars as mentioned earlier, which are born from the same molecular cloud. Therefore, they have similar age and most importantly chemical composition, because the chemical composition can also drive the evolution of a star in a slightly different way. Open clusters are younger, and they are generally found to be a few mega years old, and in some cases a few billion years old, but most of them are less than 10 billion years. And since these are younger, there are also remnants of gas and dust present in these clusters, because this is the material from which these stars formed. And the picture shown here is of NGC 7455, which is also known as the jewel box cluster. The other type of cluster is the globular clusters, and there are nearly 150 globular clusters known in the Milky Way. These comprise really large number of stars, from several hundred thousands to several millions of stars, and since this is a very large group of stars, this is also gravitationally bound and has a spherical appearance, where there is a higher density of stars towards the center as compared to outside. These are also very old, most of them are older than 11 billion years. Although there are a few globular clusters found close to the disk of the galaxy, most of these are located in the halo, that is above and below the galactic plane. As they are very old, there is very little gas and dust in them. So, if one wants to study the evolution of stars, as I said, the best way is to study the HR diagrams of clusters of stars, because these clusters of stars represent stars having approximately the same age. And as if we are studying stars or clusters of stars of different ages, one can get an estimate of how the evolution of stars occur. Before we go into the HR diagram of clusters, one can look at the distribution of stars in the cluster. When I say distribution of stars, I mean the mass of the stars. how are the masses, stellar masses distributed in a given clusters? It is found that in most clusters almost universally the low mass stars are much more abundant as compared to the high mass stars, and researchers have been studying this mass distribution of stars, and they have given it a specific name which is known as the initial mass function. So, because a cluster is are a group of stars which have not dissociated and they are still held together, one gets an idea of the distribution of masses in which these stars were produced in the molecular cloud. So, what is the initial mass function? Initial mass function represents the number of stars per mass bin, or since the mass range is very large, rather of log mass bin, and one can plot this number of stars as a function of the mass bin, which is shown on the right hand side, and very often it is found to have a power law form in the logarithmic plane. As we can observe that this has a negative slope, that is the low mass stars are much higher in number as compared to the high mass stars. So, what is the typical form of the power law of the initial mass function? Initial studies of these clusters were done by a number of people such as Kalo, Krupa and others, but now a large number of researchers are studying the initial mass functions, that is trying to understand the mass distribution in various clusters, because this is an empirical function, and using this empirical function one can understand more about how the molecular cloud fragments to form stars of different masses. Various effects go into this, that includes the process of fragmentation, and multiplicity of the stars could affect it, observational bias could affect the what observational results we get, and to do the interaction of the stars with the surrounding interstellar medium or other effects in the interstellar medium affect the mass of the stars. There are a number of such factors that people are investigating, but the most common form of power law that is very well accepted and applied in many places is the Scalo power law form, and this is given in the slide here. As one can see, dn is equal to n naught xi m dm. This represents the initial mass function xi m, and dn by dm represents the number of stars per mass bin, and n naught is the constant. So, the Scalo form of the power law shows that a single power law is not sufficient to explain the distribution of masses, and therefore, for different mass ranges different power laws were used for, but in all the cases it is found to be negative. For stars with masses greater than 10 solar mass, the power law goes as m power minus 2.45. Between 1 and 10 solar masses, this the initial mass function goes as m power minus 3.27, and for lower mass stars less than 0.2 it was found to be minus 1.83. Thus, clusters have a large range of masses from very low mass to very large mass, but of course, the large mass stars are rare, and one such distribution of stars is shown on the right hand side. When I say distribution, a number of clusters are shown, and the power laws which are fitted are also indicated by the dashed lines. So, as the cluster evolves, it has been found that the initial mass function, also the power laws that are used to understand the initial mass function, that power law is found to vary slightly. Now, in fact, people are also looking at the initial mass function of the cores, that is even before the stars have formed, the molecular cloud can fragment into cores. People are trying to understand what is the initial mass function of the cores from which the stars are going to be formed. So, if as the stars are of a range of masses in a given cluster, if one plots them on an HR diagram, then how would the HR diagram look, because this represents stars of a given age. In this slide is shown the Gaia HR diagram of nearly 32 open clusters, and here the color coding represents the age. The blue ones, the blue dots represent stars which are young, that means that they represent clusters which are young, and with age progressively the red dots represent stars in the older open clusters. So, from this figure one can see that the younger open clusters extend all across the diagonal band. They mostly comprise of only main sequence stars, and they have stars which have higher effective temperature to very low effective temperature. When I say higher effective temperature, that is the left side, that is they have higher masses also as compared to the ones on the right hand side which have lower effective temperature, because here we are talking only about main sequence stars, that is the stars which are fusing hydrogen to helium in their cores. Now, the older clusters seem to show a turn off. Now, we will try to understand why this turn off happens. What happens that the older clusters have this kind of turn off, they move away from the main sequence band and start moving towards the giant region of the HR diagram. And we also observe that these clusters, that is the older clusters, hardly have any massive stars. So, what does this infer? What can we understand from this kind of HR diagram? This figure, for example, again shows the HR diagram of a number of open clusters, but this is a schematic diagram where the lines, colored lines are used to indicate the region that the stars occupy. And as one can see, there are a number of open clusters, and some of them have high mass, and a large number of them are actually having a turn off which is away from the main sequence towards the giant. Would this mean that the massive stars move off the main sequence first? Yes, it is so, because this is related to the main sequence lifetime of massive stars, or the scale. One can have a scaling relation of the main sequence lifetime to the mass of the star. Main sequence lifetime is given by the energy in the system to the luminosity. That will tell you how long the main sequence star would live. Now, this energy is in the main sequence star is because of production from nuclear process. So, the energy is directly proportional to mass, and therefore, E by L is proportional to m power 1 minus alpha. Alpha here represents the mass luminosity relation, and the most commonly used value of alpha is 4, and therefore, the lifetime of the main sequence star goes as 1 by m cube. This would mean that a massive star would have a much smaller main sequence lifetime as compared to a low mass star, and these kind of scaling relations are used to get quick estimates of the time that a star spends in its main sequence phase. For example, we know that the main sequence lifetime of the sun is of the order of 10 billion years. Now, if we use these scaling relations, we can immediately do quick calculation and find that the main sequence lifetime of a 10 solar mass star will be 3 magnitudes lower. That is, it will spend around 10 million years in its main sequence lifetime, unlike the sun. And a lower mass star, such as a 0.1 solar mass star, will spend 3 orders of magnitude more time in the main sequence phase. That is, it will continue to remain in the main sequence phase for 10 power 13 years, that is 10,000 billion years, as compared to the 10 billion years that a sun spends on the main sequence phase. Now, this plot shows HR diagram of globular clusters, and we observe that the HR diagram of globular clusters look quite different from what was observed for open clusters. This has to do with the nature of stars in the globular clusters. We know that the globular clusters are much older than the open clusters. So, the effect of the age would mean that the stars occupy different regions in the HR diagram. A number of branches which can be seen in the HR diagram of globular clusters, and as we move along we will see what these different branches represent. Here, of course, the color coding is according to metallicity, and therefore, one can see that clusters with different metallicity occupy different regions on the HR diagram. Although the pattern seems to be the same, they occupy different regions, which goes on to say that the metallicity does have an effect on how the stars evolve. this slide shows a comparison of the open clusters and the globular clusters using the Gaia filters, and one can clearly see that in the open clusters most of the stars are in the main sequence band, and in the globular clusters there are few stars in the main sequence band and a large number of stars which are present in the branch towards the giant and other branches which one can see. So, does this point towards the evolution? Since we know that globular clusters are much older than open clusters, can we use this to understand the evolution of stars? This diagram also shows in the same plot one open cluster and one globular cluster, and one can clearly see that the open cluster, the main sequence band extends further than the globular cluster. However, in both cases one can see a group of stars which seem to be moving off the main sequence band. So, let us try to understand how a star evolves, what factors go into the evolution of a star and what is the time scale of evolution. This because main sequence stars are powered by the nuclear reactions that are happening at the very core. The time scale of evolution depends on the rate at which this nuclear fuel is consumed. This in turn is related to the mass of the star. The conditions at the very core where the nuclear reactions occur, that is the temperature, pressure, density, composition, they all decide the evolution because the most evolved part of the star can be considered to be the very center, because this is where the composition is changing. In order to understand evolution, one has to understand the physics, how material or matter behaves under conditions of different temperature, density and composition, how the energy is produced, which is already seen, and how it is transferred to the surface, and how this energy is transferred from the surface out into space, that is what we receive, the luminosity. So, all these processes go in are required if we are to have an understanding of how stars evolve. And in this respect, HR diagrams provide a very important constraint. Using this HR diagram, one can get stars of different evolutionary stages. For a given evolutionary stage, depending on its surface temperature and luminosity, the star will be located at a different point in the HR diagram. And what is the most important characteristic that drives the evolution of star? This is the mass of the star, because the mass of the star decides the conditions, physical conditions at the very core. So, first we will consider the evolution of a one solar mass star, that is, in other words, we will consider the evolution of sun. So, at the very core during the main sequence phase, the sun is undergoing nuclear reactions via the PP chain and producing helium. Now, which part of the core will actually undergo this nuclear fusion is decided by the temperature and pressure conditions, density conditions, which in turn is decided by the mass. And therefore, a certain fraction of the core will have the conditions for the nuclear reactions to occur. But what happens if the hydrogen in this region, in this core region, has fused to helium, and in the other regions the conditions are not high enough for the fusion to occur? Then the nuclear reactions would stop, and the star would have a helium core and would have a large part of the star would be hydrogen. Now, the nuclear energy generation process has stopped, there is no more nuclear energy generation, the core starts contracting gravitationally and starts getting heated up. This happens on Kelvin-Helmholtz time scales, and along with the core, the layers above the core, when I am saying the core, I am talking about the helium ash that is present in the center. The layers above it, which are made of which are hydrogen, they also contract along with this, and this contraction heats up the layers which are close to the core. Now, in these layers just above the core, the temperature and pressure conditions reach such that the hydrogen fusion can be initiated. So, hydrogen now starts burning in a shell around the core. Now, there is a source of energy generation. As the core shrinks, more and more helium is added from the shell onto the core, and as more helium is added onto the core, this again helps in the further gravitational collapse. This gravitational collapse in turn pulls the edges of the hydrogen burning shell towards it, and to counteract this gravitational pull from the core, more and more hydrogen starts burning in the shell and more energy is being produced. One has to remember that the amount of hydrogen that is being burnt in the shell is much more than what was being burnt in the core. Therefore, much more energy is being produced as compared to what was produced in the main sequence phase. Now, this is what is happening near the core, but how is this energy being transferred to the surface? Because observational effects will be visible only on the surface. So, this has to do with the energy transfer process from the core to the surface. So, initially as more and more energy is being transferred outside, the star begins to expand. As it begins to expand, the surface temperature drops. As more and more energy is being generated in the shell, more and more the star continues to expand, but the surface temperature cannot drop below a certain value. That is because at the surface the free streaming of photons is at the surface, which is responsible for the luminosity, is constrained by the opacity effects, and beyond some point of time the temperature cannot arbitrarily fall to very low values, and the an outer envelope no longer is radiative. Now, it starts becoming convective, because it is found that the convection energy process is more efficient in transferring heat to the surface because of opacity effects rather than the radiation. And this phase is shown through an HR diagram as well as through schematic. In the schematic, on the left hand side, we see the subfigure A shows the main sequence phase where the hydrogen is burning in the core, and one can see the photosphere. Photosphere is the region where most of the photons that we see originate, and on in the B figure, one sees the post main sequence phase when the hydrogen is burning in a shell around the core and the helium core is contracting. The energy is more and more energy is being produced, as a consequence of which the photosphere expands. And in the HR diagram on the right, one can see the path that one solar mass star will take after it has fused hydrogen. Surface temperature drops till it cannot drop below a certain value as a result of opacity effects, and then the temperature, the surface temperature remains more or less constant, but as the energy production is increasing in the shell, the luminosity increases. This is when the envelope becomes convective. Because of the turbulence, the deep layers, the layers which are deep come on the surface. So, there is mixing which is happening in the envelope. Therefore, the composition of star is slightly different towards the interior as compared to outside because of nuclear processing. This mixing happens during this phase. This phase is known as the red giant phase. This is known as the dredge up phase, and this mixing up of layers. And this red giant phase lasts about a billion years. As the star, while the star is traversing towards the red giant phase, that is known as the subgiant phase, when the contraction happens. In the red giant phase, the envelope continues to increase in size. It can become, for example, for sun, it can go as large as 50 times the solar radius. This is what is happening at the envelope. What happens at the core? At the core continues, the helium core, more and more ash from the hydrogen burning shell. When I say hydrogen burning shell, I actually mean the fusion of hydrogen. The fusion of hydrogen, the product is helium, which is added continuously to the core. It contracts, the density starts becoming so high, but the temperature is not very high. The temperature is still of the order of 20 million Kelvin. The density is so high that certain quantum mechanical effects start to appear. This is known as degeneracy, and the matter in this state no longer behaves in the way that you expect classical matter to behave. When I say classical matter, I mean according to the Maxwell-Boltzmann distribution. So, when the matter is in a Maxwell-Boltzmann distribution, an ideal gas, as you increase the temperature, its velocities, the thermal motion also increases. Consequently, there is higher thermal pressure. That is, the effect of the increase in temperature is also to increase the pressure. This effect is not seen in a degenerate matter, where the quantum mechanical effects dominate. Before we go into understanding about this degenerate matter and understanding the further evolutionary stages. One can look at the schematic of the red giant phase. Here on the left is shown the core, and the envelope is shown very clearly, which is mostly convective. It is very large also, and on the right is shown the core, where at the center you have a degenerate helium core, and you have a hydrogen burning shell just outside the degenerate core. Now, what happens in the degenerate core? So, if the gas is thermal or classical, it behaves according to the classical Maxwell-Boltzmann distribution, then it has random thermal motions. Now, what would happen if the temperature were reduced and it was brought to 0 temperature? Now, if most of the system is comprised of fermions, in this case electrons, then all of them cannot occupy the 0 energy state because they are governed by the Pauli exclusion principle. And the Pauli exclusion principle states that no two electrons can have the same quantum mechanical state. Therefore, there are a number of energy levels. There are a number of energy levels which the electrons can occupy, and in a bound system, and therefore, the energy levels are filled up with the pairs of electrons of opposite spin. Now, how is this quantum mechanical effect related to the core of a star, where the temperatures are very high? It is not 0. There is another effect which plays a very important role. That principle is the Heisenberg's uncertainty principle, which states that it is not possible to define the position and momentum of a particle to an accuracy which is better than Planck's constant. That is, delta x delta p should be greater than or equal to h bar. Now, if this is of course in one dimension, in 3 dimensions it would mean that this Heisenberg's uncertainty principle translates to the uncertainty volume multiplied with the 3D momentum uncertainty, which is greater than h bar cube, or the uncertainty in the 3D momentum is greater than or equal to the h bar cube by the uncertainty in volume. So, how is this Heisenberg's uncertainty principle related to the stellar cores? Now, this is related because the density of matter is very high. Once the density of matter is very high, even if the temperature is high enough, this causes the momentum states to be very far apart. One can think of the uncertainty principle in the following way. In the momentum space, the electrons will occupy energy levels which are separated by h bar cube by delta v. So, as delta v starts becoming smaller and smaller, the grid of the momentum levels start becoming very far apart. So, the electrons start occupying the lower energy levels, but they are forced to occupy even the higher energy levels according to the Pauli exclusion principle. Consequently, even though they are they have a pressure associated with it, and this pressure is because they are forced to occupy the higher momentum states. So, let us understand degeneracy pressure. I will first draw the energy levels that the electrons could occupy. When the system is classical, they occupy very high energy levels, closely spaced. The electrons could occupy any of these energy levels. But as the temperature goes to 0, the electrons start occupying the lower energy levels, and two electrons are present in each energy level. This is a consequence of the Pauli exclusion principle. For temperature T equal to 0, all the energy levels, lower energy levels are filled up till an energy level that is given by the Fermi energy. This Fermi energy is decided by the number of electrons present in the system. For the case of a star, the temperature is not 0. However, now what one has is that the energy levels are very spaced very far apart, because the energy levels are decided by the Heisenberg's uncertainty principle, which is given by this relation. So, as delta v becomes very small, the momentum spacings or the energy spacing start becoming very large. So, the electrons now occupy the levels, but as a result, although they may not, the system may not be completely degenerate. Since the energy levels are very far apart, they start occupying the subsequent energy levels from the bottom. The consequence of this is that these the momentums or the pressure is decided by the velocity. Velocity is related to the momentum. So, the momentum levels is, since they are occupying higher and higher momentum levels which are spaced very far apart, there is a pressure because of this effect. This effect is known as the degeneracy pressure. This is a kind of misnomer because the electrons are not degenerate, they do not lie in the same energy level, they occupy different energy levels, but this is how this pressure has been named, this quantum mechanical pressure. So, at higher temperature, in the case of stars for example, the temperatures are not very low, it can be as high as a few million Kelvin, I mean 20 million Kelvin. But even in this case, the densities are so high that the system becomes degenerate. What is the consequence of this degeneracy pressure? An important consequence of this degeneracy pressure is that the system does not have a feedback mechanism to manage the heat. So, in a classical or thermal system, as and when one gives more and more energy is being produced, or let us say heat is given to the system, the electrons can it is a classical system, the pressure is higher for a gas with higher temperature, this is the thermal pressure. However, in a degenerate system, one really, if one needs to make the system classical, one needs to remove the electrons from all these lower energy levels and move them to very high energy levels. That requires a lot of energy, because the energy levels are also very far apart in the degenerate space as a consequence of the contraction. And according to quantum mechanics, for a finite temperature, the occupation probability of an electron for a given state is given by the Fermi-Dirac statistics, which is well known, and it is partially degenerate for a finite temperature. So, in stars the temperature could be high, but the density is very high, and therefore, the delta QP or the instantaneous momentum is very large and the grid spacing is large. So, electrons are forced to occupy higher momentum states, and this gives rise to the degeneracy pressure. As mentioned earlier, the temperature dependence is very weak, and one can derive an expression for the degeneracy pressure. For a completely degenerate gas, Subramaniam Chandrasekhar was the first to derive this expression. And for a fully degenerate gas, one finds that the pressure goes as a power of the mass density, and this power is 5/3 when the system is non-relativistic. That is the energy levels that the electrons occupy is such that the electrons exert pressure, but they are moving at non-relativistic speed. This degeneracy pressure for non-relativistic degenerate gas is given as P equal to K1 mass density by mu e power 5/3. Here mu e is related to the average number of free electrons per nucleon. So, in a system which is fully ionized, for example, a hydrogen plasma, mu e would be roughly 5, but this number changes for the system which is made up of helium nuclei and electrons. And when we say the system is degenerate, we mean with respect to the electrons, because the mass is an important factor that goes in this factor K1 which is here, and the electrons are the first to achieve the degeneracy. If the nucleons are fermions, they can also undergo degeneracy pressure, but because of the larger mass effect, this is achieved at much higher densities. So, this is what happens in the core of a one solar mass star, a helium core. While the system is becoming degenerate because of probabilistic processes, a small amount of helium fusion is initiated by the triple alpha reaction. But this generates heat, but this heat is unable to get transferred outside. That is because usually in a thermal gas, as more and more heat is generated, it expands. and as it expands this it gets cooled, and then it can the system can come back to its state of equilibrium. However, in case of a degenerate gas, it is unable to dispense of this heat, because the energy would just probably raise the outermost electrons to higher energy levels. As the matter in the core is degenerate, the temperature does not rise, and therefore, it does not increase the pressure, and as a result the expansion also does not occur. Now, as the heat is increasing, the temperature in the core continues to rise, because this heat cannot be transferred outside the core. I mean, the amount of heat transfer is very less because of weak temperature dependence, and this heat further fuels the rate of helium burning. When I say helium burning, fusing of helium to carbon. And this reaction, particularly the fusing of helium to carbon, has a very high temperature dependence. In fact, we have seen that it goes as a temperature power 41, 41st power, which means the rate of the reaction steeply rises with temperature. More and more helium continues to burn, producing more and more heat. And as a result, so much of heat is generated, or energy is generated, that the electrons are transferred to the outer energy levels, that is, the system becomes classical and the degeneracy is lifted. This process is known as the helium flash. So, the helium fusing to carbon oxygen begins as a helium flash in low mass stars. However, this is what is a consequence of our understanding of the state of matter and our understanding of how matter behaves under these conditions. It is very difficult to observe a helium flash, because although a large amount of energy is generated which is transferred outside, this energy is all absorbed by the overlying hydrogen layers, and its effect cannot be seen on the surface. But because of the conditions, it is expected that low mass stars do pass through this helium flash phase. Now, once the helium flash has occurred, the temperatures are now again very high, the core is thermal, helium is stably burning or fusing to carbon in the core and in a thermal core. And as a result of the helium burning, the hydrogen burning in the shell around it becomes weakened, and as a result the luminosity decreases. Now, this phase of the star, when the helium is stably burning in the core, is known as the horizontal branch phase, and there could be layers outside which are burning hydrogen. But these are also the phases where the radius envelope is very large, and because the envelope is very large, the surface temperature is very low, surface gravity is very low, and mass loss begins to occur. There can be quite a bit of mass loss occurring. And in fact, it is found that there are one cannot predict how much mass loss will occur in this phase. Some stars undergo more mass loss as compared to the other stars, and the stars which undergo more mass loss will have a weaker helium burning in the shell as compared to the ones which have not undergone mass loss. And that is why these stars which are in this phase will lie along a horizontal branch in the HR diagram. The position of the stars in the HR diagram is decided by varying amount of mass loss. It could be the effect of age and also the effect of chemical composition. And the structure of the horizontal branch star is shown in the schematic here. On the left hand side, one can see that there is the core with a radiative envelope. Now, again the star has become, the star is smaller because the outermost layers in many cases have gone, the star has also shrunk, and in the very core you have helium stably fusing to carbon, oxygen at temperatures of the order of 100 million Kelvin. This is surrounded by a shell of helium, where there is no helium fusion, because these are regions where the temperatures and densities are not high enough for the helium fusion to occur, and surrounding this you have a shell where the hydrogen is burning. Now, what happens after the helium burning in the core is exhausted? The star again now begins to contract, that is the core which comprises of carbon oxygen contracts on Kelvin-Helmholtz time scales. And although it gets heated up, now it has compared to the earlier phase, it has lost most of its mass. At some stage the densities become so high that it becomes degenerate again, that is electron degeneracy pressure dominates, and this electron degeneracy pressure now is is now responsible for the size of the star, in the sense that in these kind of stars the carbon oxygen core, the degeneracy pressure balances the force of gravity. So, the hydrostatic equilibrium is maintained because of the degeneracy pressure. Carbon oxygen core is degenerate at the center, and further out as the core as the envelope is collapsing, just exterior to the carbon oxygen core, one has the helium shell where the temperatures could rise for helium to start burning. And so, helium starts burning in a shell, this again increases the luminosity. And beyond this, if there is sufficient matter, then you could have a shell of helium which is not burning, because the temperature and pressure conditions are not high enough for this fusion to occur. And beyond that, if there is another shell of hydrogen, this is fusing to helium. This is all governed by the temperature gradient which is present in the star. As the temperature and pressure conditions are such for the helium fusion to occur, it will occur, and if it is sufficient for the hydrogen fusion to occur, it will occur. And again in this process, more and more energy, because there is more energy production because of the double shell burning phase, that is the helium burning in a shell as well as the hydrogen burning in another shell outside, a large amount of energy is being transferred outside, and this causes the size of the star to increase by orders of magnitude, and this phase is known as the asymptotic giant branch phase. And this in the case of the sun, the size of the star can become as large as 300 solar masses. Now, the surface gravity becomes again very low, and there is a lot of mass loss which is happening. The envelope becomes convective again, and again there is a mixing of matter which occurs, and this is known as the second dredge up. Meanwhile, the core is shrinking, and the carbon oxygen core, however, reaches a state where it becomes electron degenerate, but the mass is not enough for the temperature and pressure conditions to ignite the fusion of carbon. So, for a star like the sun, the core remains the core is made up of carbon oxygen nuclei which is supported by electron degeneracy pressure. So, this core is known as the white dwarf stage. So, this is the structure schematic of the structure of an asymptotic giant branch star, and one can see that the envelope is highly convective, the size becomes much larger. And what happens in the core? On the right hand side, this can be seen, there is a degenerate carbon oxygen core which is surrounded by a helium burning shell. This is surrounded by a shell which is made up of helium ash. Further out is a shell where hydrogen is fusing to helium. So, this is a double shell burning phase or the asymptotic giant branch phase. The later stages of evolution are highly uncertain. This is because there is again enormous amount of mass loss occurring. How that energy is getting transferred to the surface, what are the physical processes occurring, they are all driven by the mass loss, the metallicity effects. Even theoretically, it is difficult to calculate what exactly would be occurring in the envelope. Observationally, these stages do not last very long, and therefore, we do not have too many observations of stars in the stage, but it is expected that these outer envelopes would be blown out, and this would form a kind of nebula around the central carbon oxygen degenerate core or the white dwarf, and this nebula is known as the is called a planetary nebula. And surrounding the white dwarf, there could be shells of material where helium nuclei is fusing, as well as shells of material where hydrogen nuclei is fusing. Over time, as this fusion comes to an end, what is left is just the carbon oxygen degenerate core. And now, as there is which is the white dwarf, this white dwarf does not have any source of energy production, and but it is very hot because of the energy which is remaining as a result of the nuclear processes. And therefore, a white dwarf which is seen, although it has no energy production going on in the core, is very hot and it appears very bright, and as a result it produces a lot of UV radiation which can ionize the nebula, the planetary nebula around it. Over time, the white dwarf cools just like a hot body which cools in a cooler environment. It becomes faint with time, and also is very less luminous. The next slide shows the entire evolutionary process through the HR diagram which is shown here. So, in the main sequence band, although the main sequence band is shown here, one can see how the evolution of sun would occur on the HR diagram. For instance, one can see that the sun first moves off the main sequence phase, it becomes a subgiant when it is contracting, and there is a hydrogen shell burning phase. Then it becomes a red giant, then the tip of the red giant is where the helium flash occurs, then it moves towards the helium core burning, which is the horizontal branch, and again after the core has fused, there is the double shell burning phase or the asymptotic giant branch phase, and the star again rises in the HR diagram because its luminosity increases. The later uncertain evolutionary stages are shown by the dashed line, which is the planetary nebula phase surrounding the white dwarf core. So, this is the evolutionary stage that a path like the sun would take as it evolves to further evolutionary stages. Now, how would, this is the case of the sun, how would higher mass stars evolve? Let us say we take intermediate mass stars such as a star which is 2 solar mass or 5 solar masses. Now, there is an important difference in how the helium burning is initiated. The stars which are greater than 2 solar masses, it is found that the temperatures in the core are high enough that the core never becomes degenerate. So, these temperatures are already of the order of 100 million Kelvin, and therefore, helium burning is initiated in the non-degenerate phase, in the thermal phase itself. So, therefore, stars which are more massive than 2 solar mass stars, it is expected will not undergo the helium flash, but the path that they will take on the HR diagram is quite similar, as one can see the HR diagram shown in this figure, which is corresponds to the evolution of a 5 solar mass star. So, there is from the ZAMS, as the core contracts, again the helium in hydrogen in the core is exhausted, there is an overall contraction. I am reiterating again, the hydrogen starts burning in a shell, which is the subgiant phase, and as more and more energy is produced, it rises up and convection takes over, then it becomes the red giant branch. Then the helium core burning is initiated at the tip of the curve which is shown there, and once the helium core burning or fusion is initiated, the star shrinks and it moves down towards the horizontal branch phase, where the core is stably burning helium to carbon oxygen. Beyond that, it moves once that is the helium burning in the core is exhausted, the star again moves up and passes through the asymptotic giant branch phase, where there is a second dredge up and it forms a planetary nebula, and finally, what is left is the very core, which is the white dwarf. However, for higher mass stars, the core may undergo further fusion stages and nucleosynthesis may proceed because the temperatures could be high enough for the generation of oxygen, neon, sodium, magnesium. It is important to remember that this is highly dictated by the mass of the star. Therefore, for a star, for example, which is having mass less than that of the sun, it may not even reach a carbon oxygen degenerate core. It may stop at a helium degenerate core, and for higher mass stars, for example, it may have you may have a carbon oxygen core along with neon and magnesium and other degenerate cores. So, medium mass stars also end up as white dwarf, but with higher mass elements. This again shows the post main sequence evolution of a 5 solar mass stars, and the table shows the various stages and the time durations. Here it is very clearly marked. This is the result of very involved computations after understanding thoroughly the physics involved and the mechanisms by which energy transfer happens from the core to the surface. And in the later stages, when there is nuclear fusion in the shells, in the giant stages, sometimes the star can become highly unstable. This is because as the fusion is occurring in the shell, as more and more energy is produced, it would try, because of the excessive pressure, it would try to lift the layers above it. But if the mass of the layers, overlying layers, is much higher, it is unable to lift. So, the temperature goes high. So, the feedback mechanism does not seem to work, or the thermal valve kind of mechanism does not work. The temperature continues to increase because the increase in pressure is not leading to increase in expansion of the layers. As a result, the temperature increases and it leads to a kind of runaway where so much energy is produced that it is able to lift the overlying layers. Once that happens, there is a lot of expansion occurring and the energy is transferred outside, and the star again comes back to its original state. It again contracts and comes back to its original state, and again it follows the same path. So, these are known as thermal pulsations, and the star appears to be variable, where it goes through these phases of higher luminosity, lower luminosity, because of these thermal pulsations. So, this of course depends on the temperature and pressure conditions which are present, and of course the mass of the star. The physics drives the generation of these kind of thermal pulses or oscillations. So, in the HR diagram, very often we see a group of stars in the giant phases and supergiant phases where the stars show a variability. That is because of the radial oscillations which are a consequence of the dynamical instability of these nuclear burning shells. So, what happens to stars which have mass more than 8 to 10 solar masses? So, it is anticipated that stars which are having mass more than 8 to 10 solar masses, there would be successive shells where of nuclear burning, where the different elements are being fused to the next successive element depending on the temperature and pressure conditions. So, for instance, if one sees the figure, the outermost one of the shells close to the outer envelope would be fusing hydrogen, then you would have you would have helium inert shell, then you would have a shell where helium is fusing, you could have a shell where carbon is fusing, you could have a shell where oxygen is fusing. This is all dictated by the temperature gradient and the mass and other conditions. So, it is expected that this for high mass stars, because it has a lot of nuclear fuel, it passes through this kind of phase, which is also known as the onion shell structure, because there are these various layers or shells where successive stages of nucleosynthesis is carried out. And of course, the final stable element is iron. So, it is expected that the core would be fusing to iron, and this iron will not undergo further nucleosynthesis because iron nucleus is the most stable nucleus. And this slide explains what I had explained earlier, that is the contracting cores of more massive stars will reach temperature for carbon ignition to occur, neon ignition to occur, magnesium, silicon and so on till iron. What happens after iron is formed at the core? It is expected that now it cannot undergo any more nucleosynthesis when it contracts because it is very stable, but as a result collapse takes over, and as a result of this collapse very high densities and very high temperatures are reached. Now, the next step of nucleosynthesis is expected to be iron photodisintegration, where photons interact with these iron nuclei to produce a large number of alpha particles. As the star undergoes further contraction, these alpha particles themselves photodisintegrate. So, all the nucleosynthesis at the core which was carried out till now is undone at this stage, and what is left at the because of the high density and temperature conditions is mostly some iron nuclei and some neutrons and electrons. And all these processes, as it is using up more and more energy, this core contracts further and further till you can have a stage where the neutrons, which are also fermions, can become degenerate. This is known as the neutron star. Now, what happens to the outer envelopes? The outer envelopes, it is not very certain what happens, but observationally it has been seen that the outer envelopes are thrown out during the formation of these kind of very compact objects like the neutron stars or the black holes, because if the core is unable to support the gravity by neutron degeneracy pressure, it can undergo further contraction and form a black hole. And the conditions, however, leading to this is not very clear, because it requires an understanding of elementary particle physics, densities and temperatures, which are difficult to speculate. We do not have a complete understanding of them. However, there are various models and a number of people are working to understand these phases. And if the final mass of the core is less than 3 solar masses, it is expected that it will become a neutron star. And if the mass of the core, this is, remember, this is not the initial mass of the star. The initial mass of the star is much higher, but most of the outer layers would have been thrown away either in the later supergiant phases or during the supernova explosion, because massive stars do not go through the AGB phase, rather they go through the supergiant phase. If we consider the evolution of stars with higher mass, the track that they follow in the HR diagram is slightly different from what has been observed for intermediate and low mass stars. Most of the these tracks are shown in the HR diagram in the figure. One can see that the tracks of the massive star, the evolutionary tracks of the massive star, as they move away from the main sequence branch, are mostly excursions to the right and to the left. This is mostly because the core contraction leads to a decrease in effective temperature, and core ignition leads to an increase in effective temperature. So, but there is not much change in the luminosity of the star during these processes. That is, for the high mass stars, one cannot see a large change in luminosity as the star evolves. This is primarily because of two reasons. Firstly, in the later stages, changes occur on relatively short time scales, and therefore, the outer envelopes do not have time to respond. And secondly, in the case of massive stars, the mass of the overlying envelope is very large. So, the changes which happen on these time scales, it is not possible for the changes to be energy changes to be transferred outside towards the surface in short time scales. Consequently, one does not see a change in luminosity which was observed for the low mass stars, that is up to 2 to 3 solar mass stars. Rather, the high mass stars pass through the supergiant phase are quite uncertain. So, this in this slide, one can see on the left figure a plot showing the modeled temperature and density conditions at the center of a massive star, and one can see that the path that the core of the star would take, that is the physical conditions at the core as the star evolves. So, the time scales are also mentioned here, and one can see that the core carbon burning phase, for example, lasts for 10 power 9 seconds, whereas the core oxygen burning phase lasts just for 10 power 7 seconds, and the successive element, the nuclear fusion, takes even less time, which suggests that the evolution of these stars happen on very fast time scales, the later evolutionary stages. As there is a lot of uncertainty, there are modeling is also currently happening in order to understand the later stages of the evolution for the low mass stars as well as for the high mass stars. For the low mass stars, it is relatively easier because these changes take place over time scales, so that there are chances for us to observe the later stages of evolution. On the other hand, for massive stars, the evolutionary time scales are very short. So, it is very difficult to observe them in the late evolutionary time scales. Modeling therefore plays a very important role in our understanding of how the stars evolve. This panel on the left shown in the slide shows the modeled evolutionary stages of stars from 0.75 solar mass to around 7 solar masses. The color coding here represents the ratio of the turbulent pressure to the core pressure. So, this color coding shows that towards the giant stage or the later stages, one sees that the convection dominates as compared to the other pressures, that is the radiation and thermal pressure. This is another set of models by an alternate group, which shows the effect of the evolutionary stage from 0.8 solar mass to 25 solar mass. The effect of metallicity is also considered in the evolutionary stage, as the numbers for across the each track represent the mass and the metallicity. And again one sees that for the low mass stars there is a change in luminosity, a drastic change in luminosity across many orders of magnitude as it evolves, whereas for the high mass stars the change in luminosity is minimal. For the massive stars, the details of the outer envelope are quite uncertain. We believe there is an ordered onion ring structure, but does it really happen like that, or is it washed away by convective mixing? This is not very clear, and unless we find ways and means to test this, it will remain in the modeling domain. Observationally, it is observed that supernova explosions leave behind neutron stars. Therefore, it is believed to a large extent that the outer envelopes are thrown out during the later stages of evolution of massive stars, and what is left at the center is either a neutron star, or in case of a more massive main sequence star, a black hole. Now, what causes this violent explosion of the outer layers? This explosion because there is a furious nuclear activity going on at the center. Again, this is not very clear, as there is furious nuclear activity going on in the envelope, and there is even considerable nuclear processing happening at the core beyond iron. And it is possible that the effect of these nuclear activity from the envelope or the processing in the core, or the effect of neutrinos and radiation in the later stages of evolution causes the explosion to occur, leading to what is observed as a supernova. And this supernova is a very violent explosion. A huge amount of energy is released, that this star in the supernova explosion stage can even outshine the entire galaxy, and a complete theoretical understanding of this is lacking at present, but there is activity from researchers in trying to understand these later evolutionary stages. This slide shows a pictorial scheme of the stellar evolution as we have discussed. So, stars are born from molecular clouds, and if it is a low mass star like the sun, then beyond the main sequence phase it expands and form a red giant phase. It goes through a asymptotic giant branch phase, and finally the outer envelopes are thrown out, where one can see a planetary nebula with a white dwarf at the center, and over time the nebula also dissipates and merges with the ambient interstellar medium, leaving solely the white dwarf behind. In the case of more massive stars, one can see that beyond the main sequence phase it passes through the supergiant phase, and beyond this the outer envelopes of the star are thrown out in a violent explosion called supernova, and what is left behind is a neutron star or a black hole. These various stages can also be seen, for example, in the HR diagram of a globular cluster, and a globular cluster being around more than 11 billion years old, one can only see the evolution of low mass stars, because the high mass stars would have evolved off the main sequence and would probably have become neutron stars and black holes. So, this is an HR diagram of the globular cluster M15, and one can see the various branches are listed out. There is the main sequence branch, and the stars which are as time passes the stars move off the main sequence. if one has a range of masses, it happens sequentially. First the most massive stars move off the main sequence because they have the shortest main sequence time scales, and subsequently the lower mass stars move off the main sequence. Thus, by even looking at the turning point of the main sequence branch, one can get an estimate of the age of the star. One can also see branches corresponding to the red giant branch, the horizontal branch, and here a set of stars called RR Lyrae are also marked. These are variable stars because of the radial pulsations discussed earlier in the presentation. With this we come to the end of this presentation. This last slide presents an astronomy periodic table where the origin of all the elements in the solar system and on earth is speculated, and this origin is listed through various color coding. One can see that an element can have more than one sources of production. You could have an element being produced either in the Big Bang fusion or an exploding massive star, an exploding white dwarf star, cosmic ray fission. It could also be because of merging neutron stars or dying low mass stars. Thank you.